continue. We're going to learn specifically about Faraday's Law of Induction. I wanted to start, though, with a couple of demonstrations just because, well, we all know physics is fun. I told you about Orsted's discovery, accidental discovery about the magnetism when we had current in a wire. And so I set up a demonstration that's essentially what he had. So we have the electric wires just running here next to the compass. And when I turn on, I'm going to have to plug it in, it turns out. When I turn on the power, which is what he did, we should see the compass move. And so he was like, whoa, right? Scientific method and process. He saw something interesting, starts experimenting. Yeah, it's reproducible. What happens if I do something like flip the direction of the wire, see what happens. And it goes the other way. And so we can see clearly that there's some kind of magnetism produced by having a current in the wire. Now, you guys can understand the direction because we've studied this in class. We have current that's coming out of the positive, so the current right now is going this direction. How do I find the direction of the magnetic field above the wire when the current's going this direction? Somebody say it out loud. Right-hand rule, what do I do? Thumb in the direction of the current, so my thumb's this way. Where do I need to have my fingers? I need to curl, and I want my tips at the location of the place I'm checking, so above. And with my fingers above, that makes the fingers were pointing that way, so the magnetic field above is that direction. Hence, it should indeed deviate so north is coming over this direction. So it's doing what we've learned. Now that's all fine and good, but we learned about coils. So here I took a nail and made it into a coil, or put a coil around it. What do we call the coil, by the way? A solenoid. How can I find the magnetic field that's made by this solenoid?
Number of loops there is.
Okay, it's actually the current times the number of loops divided by the length times that mu aught. So those things would tell us, I said the mu aught. The mu aught is if I don't have the nail in here. I don't want to take the nail out, but I will after we're done. I'll destroy it for future purposes. So right now there actually is a small residual magnetism, but not enough to pick up that paper clip. I'm going to put current through it with this baby. And situate it above it and turn on the power. And now I can pick it up, right? Turn it off, drops it. Pick it up. So it makes a pretty strong magnet just having wire wrapped around the nail. Now let's see what happens if I can take the nail out. I may not be able to take the nail out because I wound it pretty tight. I can't take it out. Well, we'll demonstrate that with this thing in a few, let's demonstrate it now and then we'll have something to look forward to explain how it works. So this here is, again, a solenoid. Now I'm going to plug this into the wall. Generally speaking, this is bad form, right? If you look at this, there's the two connectors. If I put my fingers here and plug it into the wall, well, I'll just, short out the wall socket with my body. That's bad, right? So it's a little dangerous. You have to be a little careful. There's another thing here that you have to think about that we rarely do. What is this solenoid made out of? Wire is what I was looking for. Just simple. It's wire. What's the resistance of that wire? I know you can't give me a number, but you can give me a range. Small resistance. If I put 120 volts in a small resistor, what's the current going to be? Really big, Well, if it's more than 15 amps, I'm going to blow a fuse or something. So I have to do this quickly. If I just plug it in and leave it in, it's going to blow a fuse over it. Well, circuit breaker. So I always have to do this kind of quickly. So there's no point in doing this with nothing there. I'm kind of curious. I'm going to take my paper clip and see if the paper clip is affected just like this. I've never done it before, but you know, we have to show some curiosity from time to time or we're not physicists. So let's just see what happens when I plug this in. Didn't do anything. How boring. Why don't we do something else that's equally boring probably? I have an aluminum ring. Put the aluminum ring right above it. Do it again. Okay, so it rattled a little. It arcs when I plug it in. Rattles a little. What does that tell you? Now, this is not magnetic, I should point out. It is not attracted to magnets. I took all my other magnets away, so I don't have anything to demonstrate. I guess I can do this again and show you that this is not going to be affected by it. So that's the only thing I have as proof that it's not affected by a magnet. But trust me, it's not magnetic. So this is not a magnet, but it's interacting with that thing. Something curious is happening. Something that we're going to explore later on today. Now I'm putting this in. This is a great billy club. If you have an intruder, you need to whack them upside the head. This is going to do the trick. It's made out of a whole bunch of individual little iron rods. Those iron rods are insulated so that you don't have any current that can go around in them. Why iron, you ask? Well, we are talking about magnetism. It turns out that iron is, well, ferromagnetic. So it's something that has magnetic properties. Put this back on and plug it in. What's going to happen? What do you think is going to happen? Some of you have seen this. I'm pretty sure at least Jeffrey has seen this. And right, didn't you come for college days and see this? Yeah. But somebody who hasn't seen it, what do you think is going to happen? Let's just do it. Now, if you look carefully, you would have seen two things. What was the obvious thing? It threw the ring off. So clearly putting this in made a big difference. A difference of about 1,000 times the strength. So before it was just rattling, now it throws it off easily. What was the other thing that happened? This here got yanked up. It made the magnetic field strong enough that it easily picked it up. So putting this in clearly made a much stronger magnetic field. We have two lines of evidence here. One is just the normal what a magnet does, and the other one is it threw that thing off. So we can see the magnetic field increase, and we don't have anything to really understand why it threw that thing off. So I'll have to go through my lecture, and when we get near the end of the lecture, then we'll be able to understand why this was thrown in the air. Okay. The definition of the permeability of free space. The permeability of free space is defined as this number, 4 pi times 10 to the minus 7 newtons per ampere squared. I think I wrote something different for my units yesterday in class. I had Teslas in there, and I'm pretty sure my units were also correct. But these are, at least according to what I saw when I wrote down, the standard units. The ampere is actually defined as the current necessary to make two wires that are separated by 1 meter produce a 4 times 10 to the minus 7 newtons per meter between them. So that's a force per unit length. Now we've been talking about the force due to magnetic fields, and you had, for instance, a problem that had 3 wires like this, and you had to find the net force in the direction of the net force on the magnitude and the direction on each of the wires. And the way I told people to do it, because that's the way we were at that point, was that you have each wire is going to make a magnetic field. So for instance, this one here, I'll change the color. That X means that the current is going into the page. So using my right hand rule, the current's going to be making circles that are going clockwise for the magnetic field. So the magnetic field due to that, so that was the magnetic field due to C. B is also in, so the magnetic field due to B is going to be doing the same thing. Magnetic field due to B. And the magnetic field due to A. Since A is coming out, then you have coming out and it's going the other way. It's the magnetic field due to A is like that. And then I told you, you have those magnetic fields. You need to calculate their magnitudes. You need to add them as vectors because each one has a direction to find the total magnetic field, magnitude and direction. And then you're finally ready to find the force. The force on wire A is equal to current A times length across the magnetic field that exists in that location. So after you've calculated the magnetic field direction and magnitude, you can do this problem. Well, if it's only two wires, it becomes somewhat simpler. If I have two wires, let's say that we have currents both coming out. If the current's coming out of both wires, what direction is the magnetic field going around those wires as we view it from above? Is it going clockwise or counterclockwise? As viewed from above, that is counterclockwise. So we have the magnetic field is going like this. And I'm just going to do the magnetic field due to one of them. So if I call this A, then this is magnetic field due to A. And of course, my symmetry is a little bit failed because this is at the, that's less failure on the symmetry. So that's the magnetic field caused by A. Now I have a current A and a current B. And so if I want to look at the force on wire B, I only have one wire, so it's easier. What direction is the force going to be? Given the equation, force is equal to IL cross B. What? Alex isn't here yet, so I'll go over to Christian. Force is IL cross B. If I want to find the force on wire B there due to the magnetic field created by wire A, how do I use the right-hand rule to find the direction of that force?
It would be with the thumb is the direction of the force.
Right, the thumb is the direction of the answer.
Okay. So finger or index finger with the length.
Right.
And
So
then
that would be coming out. And then the middle finger?
going towards the other, the only big thumb.
The only thing left, which is magnetic field.
Yeah.
So we've got our index finger coming out, middle finger going up, and my thumb is pointing toward wire A. And so with the currents going the same direction, and I'm going to double check here. With currents going the same direction, my force is just going to be attractive. I called it force of A on B. Bad. So the force is attractive, and then if I want to find the magnitude of the force, it's going to be equal to current B, because I was looking at wire B, multiplied by the length of the wire, multiplied by the magnetic field, which is going to be mu watt current A over 2 pi separation. So I'm just going to put R here for the separation. And then I have the last thing. We're multiplying perpendicular components. the direction of my wire was perpendicular to the magnetic field, so that's times 1 for the cross product, how much is perpendicular. We usually simplify this to say the force between the two wires but it's multiplied by that L thing. What's the length of the wire? Well, our equation is actually truly only valid if it's an infinite length wire, which means then our force would have to be infinite. So what we do is we divide both sides by L. And we say the magnitude of the force per unit length is equal to mu naught current 1, current 2 over 2 pi separation. So the second way you could have done that problem would have been to calculate the force vector between each pair of wires and then add the force vectors, because you have 2 pairs when you look at one wire, add those 2 force vectors to find the magnitude and the direction. In terms of work, they're exactly the same amount of work. So there's no difference in doing it one way or the other for that homework problem. If it's just one pair of wires, well, then it's going to be generally simpler to do this, which is combining the 2 pieces into one. So if I have 2 wires that are very long, separated by 1 meter, and I put the same current through both wires, as I raise the current, when I get to the point where I have 2 times 10 to the minus 7 newtons per meter between them, then I know, boom, I've hit 1 amp. And so this is a very reproducible standard for defining what an amp is. And that's why it's the standard for defining an amp. It's reproducible. Now, we did 2 wires going the same direction had an attractive force. What if they were going opposite directions, if currents were going opposite directions? It'd be repulsive. If you look at this here, this is a part of a circuit, so the current goes one direction on one side and the opposite direction on the other side. The current's always going opposite directions here, which means that there's always a force trying to push the wires apart. What if the wires were perpendicular? Go ahead and say it louder, Erika.
I'd say like they multiply each other.
You multiply each other. Looks like multiply.
No, it's just that like when the equation, like because they're constant.
Well, we have that cross product. The magnetic field perpendicular to the length. Well, the magnetic field due to a current in this wire is going to be going like this, and it's going to be parallel to the length. So what's the cross product if I have the magnetic field is parallel to the length? 0. Hence, the force between the wires like this is 0. Now, this is actually important if you're doing something like putting wiring in your house. In your house, you have electrical wire, so you can turn on the lights in the kitchen, run the, TV, whatever. But then you also have data wires for your internet. Used to be you had them for phone. When I bought my house 15 years ago, I wired in both phone lines and internet lines everywhere. Well, the electric fields produced by the power lines can cause interference on your data lines. Nobody wants that. So how can you avoid that? If you make them so they cross at perpendicular angles, you'll have very little interaction. If you make them parallel, you'll have significant interaction and interference. So that's something I had to try to do is make sure, okay, I've got to cross the power line. I'm not going to go parallel with it, not just going to cross it sliding. I'm going to come like this, go straight across, and then go on the way I want to go. That way you minimize your effects. There's other things that we do. We wrap the wires. I used to buy high twist telephone cables, so they would be wrapped so I'd have better data throughput on my DSL line. All has to do with this right here. Now, motional EMF, not to be confused with emotional EMF at all. Motional EMF, EMF, electromotive force. We talked about that when we talked about batteries. We learned that it was a nonsensical term in the case of a battery. In this case, it actually makes more sense. If I have a rod here, and I push that rod through a magnetic field, I could look at an individual charge, like an electron as illustrated in this picture. As the electron is moving, it has a velocity, it has a charge, it's in a magnetic field, there's going to be a force on it. And so using our force equation, force is equal to Q V cross B, I can calculate how big the force is going to be on that charge. And so there's going to be a force pushing the charge, and that's going to create an electric field because I will end up having a bunch of electrons down here leaving a positive charge here. And so that's going to make an electric field and a voltage difference. For my nice uniform rod like this, it'll be a uniform electric field, and we'll have, oh, let me put L here. The voltage difference, that's not an L. The voltage difference from top to bottom is going to be the electric field that's created times the length of the rod. And so how big is that electric field? How are all those things going to come together? That's what the motional EMF is talking about. It's talking about how much voltage difference you create by moving the charge or the rod through the magnetic field. So how do we calculate that value? I didn't need to have the slide that was in between. I don't know what I was thinking. And so here I've gone back to an equation we saw before. We did the same thing when we did the Hall effect, because guess what? This is effectively the same thing as the Hall effect. We're going to have the force on the electron, on any electron in this rod, is the charge of the electron times the electric field plus the force of magnetism, the QV cross B. And if it's in equilibrium, right, we get it going when we reach equilibrium at constant speed, the voltage should reach a final state, then we should have those two equal to each other, which tells us our electric field is minus V cross B. Well, we set our velocity perpendicular to the magnetic field, so that's just going to be minus VB in magnitude. And so we have E is equal to the electric field magnitude is equal to V times B magnitude. Here I put the sine theta because you didn't have to have things parallel. And so the voltage difference is EL is equal to, just put in that E as VB, VBL, and then sine of the angle if you're not perpendicular. So what we have now is a way of calculating the voltage difference of having the rod going through the magnetic field. So for instance, a homework problem that I think I assigned is due in tomorrow's homework. You have an airplane flying through the air and there's a magnetic field. Yeah, there's a magnetic field. That's going to create a voltage difference from one side of the wing to the other. You could use this to, charge your iPhone. It's not a limitless source of energy because, of course, you have to make the airplane move to make this all happen, and that takes jet fuel, which is an energy. It's just recovering some of the energy from the fueling process if you use it to charge your iPhone. This gives us a very simple kind of generator process. Here we have a rod. You pull that rod, and because you're pulling that rod, it's creating that motional EMF, which is VBL, if everything's perpendicular. And so you have that voltage, a resistance using Ohm's Law. The current is going to be the voltage divided by resistance. So if your voltage, or EMF, is equal to speed times magnetic field times the length of the rod, then the current is speed times magnetic field times the length of the rod divided by resistance, as shown here. So, that resistor could be whatever the resistance is in my iPhone. And That rod could be the wings of my airplane. I just have a wire connected to each side of the wing, and away we go. It's a beautiful thing except for one thing. You have to bring the wires back to your iPhone, and you know what you're doing then? You're creating a reverse voltage, so then that voltage is zero by the time you bring them together. Yeah, that's a little bit of a bummer. Okay, first of our clicker questions. Where does the electric energy come from in the problem of this rod moving to create current that is dissipated through this resistor? Look who sneaks in the back door.
Are we going to have another clicker question?
We should.
Okay, can I have it?
I prefer you didn't at this point because we're in the middle of class. Okay, Brittany. You getting there, Brittany?
Oh, sorry.
All right. Brittany made sure we didn't have a tie. So where does the electric energy come from? There are two distinctly different answers here. Bimodal distribution. So talk to your neighbors. Alex, you're going to have to find a neighbor. See what kind of conclusion you can come to when you talk to others.
Yes.
Okay, go ahead and answer a second time. Okay, this time around, we have a very different answer. So we had a majority before that said it came from energy stored in the magnetic field. Now we have a majority that says that it's work done to move the rod. Now, instead of calling on somebody, I'll start with the easy answer. You don't have any energy produced if you don't have a magnetic field. And so the magnetic field has to be part of it. The one I prefer is the one you shifted to, that you did the work by moving the rod, and the work done to move the rod is extracted as the energy in that charge. But you don't have that without the magnetic field. So this is the kind of question I wouldn't put on a test because you can argue either one of those answers. Well, one of them is a more direct answer. The work you put in is the energy that comes out. But the other one is an important part of the process. So why do I ask a question like this in class if I wouldn't ask it on a test? Because it helps us to think things through and to classify what is going on. Because after all, in physics, that's what we're looking for, right? Understanding what's going on. Now, a simple example. What I'm asking is, what's the current going to be in this loop? So what you have here is a square loop. Don't worry that it's a slightly different color in the center. It's just a loop of wire. So think of it like this. And it's moving, and it's initially in a region with no magnetic field, and then it enters a region with a magnetic field. So here, there's magnetic field on one side, not on the other. Is there going to be a current in case B here? Yay or nay? I had to check, make sure what my next slide was. Okay, let's do an informal poll. This is one where you have to raise your hands instead of use clickers. How many people say that there is a current in case B? 1, 2, 3, 4, 5.
What do you mean by
6.
case B?
Case B. Okay, case 2. Sorry, case 2. This one. I saw your photograph. Okay, we have about 7. How many people say no current here? Okay, about 6 there. Okay, that's good. We at least had 13 people with an answer. We still have, 7 people without an answer. But at least 13 people were willing to put themselves out there. Now, I'm not going to call anyone for this. I will explain the answer. In this case, oh, come on. In this case, this side is moving into a magnetic field. Moving in a magnetic field, you're going to have an induced EMF. You're going to have the charge, the electrons are going to be pushed, right? If you do the V cross B, V is like this, B is like that. You have upward for V cross B. Since it's electrons that can move, electrons are going to go down. A current is going to flow upward. Now, if you look at the top here, this one here is what I should look at. If you look at the top, this part's a magnetic field, this part's a magnetic field. If you do V cross B on those, you're going to be making currents going, you're going to try to make currents that are going perpendicular to the wire. That's not going to make a current because charge can't flow perpendicular to that wire. So only this is going to be making a current. Over here, you're not in a magnetic field, no current being produced. Hence, this here will have a net current that's going counterclockwise. Now, what about this case here, case 3, when the entire loop is in a magnetic field and it's moving? Then what's going to happen? Okay, zero current. Why zero current now when there was not a zero current here?
Because the side on the left is going to create a clockwise current and the side on the right is going to create a counterclockwise.
Right. One's trying to make clockwise, one's trying to make counterclockwise. Like I was saying with charging your iPhone on the airplane, if you try to charge your iPhone on the airplane, your wires have to come back. The only way to really do it would be to have some kind of magnetic shielding on the return wires so you don't have the reverse voltage being produced. Okay, what about case 4, where it's leaving the magnetic field? Is there a current? Okay, we got people saying yes. Why would there be a current in case 4? Yeah, they're not canceling each other out. You have this one here that's trying to make a clockwise current and nothing here, so this one will have a clockwise current. So this had a counterclockwise current, no current, counterclockwise, no current, clockwise. And then we're all out, nothing happens in 5. Okay, clicker question. Giving you a second, it's not allowing you to answer yet. Now you can answer. What had to occur for an EMF to form in a wire within a constant magnetic field? Notice it doesn't say a loop, it says a wire. Oh, it did. It says 18 people answered. Okay, it's open again. See if it says it's closed. Yeah, looks good so far. Okay. All right. We once again had kind of a cluster there with the two most common answers being diametrically opposed to each other in idea. So once again, talk to your neighbors about which one should be the correct answer here.
Right?
Yes, approximately.
Okay, go ahead and answer again. Okay. What we had was 3 people who switched. So we didn't get ourselves really any closer to correct, did we? Amanda. When you hear audible sigh of relief from other people, that's probably not a good sign. It means your life is not as easy as you're hoping. What do you got, Amanda?
Well, we were talking and thinking that because when they move perpendicular, the charges would kind of cancel each other out, and so it wouldn't be able to work right. But I'm not really sure.
Okay, let's go to this picture here. We had, well, no, let's go to the first one I did, this one here. The force on the charge that's making all of this happen is QV cross B. Your velocity needs to be perpendicular to the magnetic field. So the velocity has to be perpendicular to the magnetic field. What about the direction of our rod? It also needs to be perpendicular to the magnetic field. We need both of those. So it's going to have some perpendicularity no matter which one it asked. So the wire must be perpendicular to the magnetic field because you're not going to move charge parallel to the magnetic field, only perpendicular. So the wire has to be perpendicular to the magnetic field or have a perpendicular component, right? If it's 30 degrees from the magnetic field, there's a component that's parallel and a component that's perpendicular. As well as the velocity has to be perpendicular. So all of this brings us to how electric generators work. Now, before I get into the electric generator, I want to go to Faraday's Law of Induction. So I skipped a bunch of slides that I should go back to. Michael Faraday in 1831 discovered that we could basically produce voltage with with a magnetic field if we have a conductor that's moving in a magnetic field. And we can have a changing magnetic field do the same thing. So it's not just having the conductor move, having a changing magnetic field is the same thing. So he came up with a law to deal with this. Here's an example of changing magnetic field. You have the same size loop and the magnetic field gets stronger. I'm just going to go straight to the law, maybe. Here's the law. Faraday's law of induction, this thing in the purple box, says that the voltage produced is minus. That minus sign is for direction. And I will refer to Lenz's law for the direction. So as far as I'm concerned, that minus sign is really not important to us, except to remind us we need to check the direction of the current. Right? Mathematically, yes, it's important. Mathematically, it's minus derivative of the flux with respect to time. What is that flux? That's the symbol phi, and we did electric flux in the past. Go ahead.
And it's electric field times area.
Okay? The electric flux was electric field dotted with the area. Right? It was the electric field that was parallel to the area. And you're like, parallel to the area, what does that mean? It means the normal direction for the area is the direction we assign to the area. So for this tabletop, the electric flux would be the electric field coming through the tabletop. For magnetic flux, it's the magnetic field coming through the tabletop. Same calculation, it's magnetic field dot area. So we have to calculate the magnetic field through the surface, and then the EMF is just the rate at which that's changing. That's what Faraday's law says. Now, we've already learned for a solenoid, if I have a current that's going like this in a loop, that's creating a magnetic field. In what direction is the magnetic field in the center of this loop? If current is going the way my finger's rotating, which is counterclockwise. It's going toward you. That's right. Right hand rule. You wrap your fingers the direction the current's going. The magnetic field in the center is going toward you. Lenz's law, which works with Faraday's law of induction, says that the direction that the current will flow is the opposite direction of the change in flux. It's trying to maintain a constant flux. So when I put this on here, if we start with no magnetic field, and suddenly the magnetic field goes strongly upward, then Lenz's law says it's going to induce a current in that loop that's opposing the change in flux. So since it went from no magnetic flux to magnetic flux due to an upward magnetic field, the induced magnetic field is going to be downward. And of course, if I have an upward force and an upward magnetic field and an induced downward magnetic field, opposites attract, likes, north and north, repel. And so there's going to be a repulsive force as you go from zero magnetic field to building a strong magnetic field here. And that repulse is what throws this off. Now, the fact is, this is changing 60 times per second the direction of the magnetic field, but the initial kick is the important part here. It would probably be better if I plugged it into a 120 volt battery, then it'd be DC, but I don't have a 120 volt battery. So I just plug it in the wall. So Faraday's law says that we can calculate the induced voltage by looking at the rate at which the magnetic flux is changing. Now I'm just going to go back to where I skipped over because it'll just be faster to go through this material now that we've done that. So an electric generator. An electric generator, you know what that looks like? It looks exactly the same as a picture of an electric motor. It's exactly the same design. Now, you have generators that are built to be optimized for generating electricity. and you have motors, I hope I said generators that are optimized for generating electricity, motors that are optimized for being motors. So typically they're not going to look exactly the same, but a motor will work as a generator and vice versa. So if you go back to the early days of automobiles, how'd you start the car? This is before I was born, just for reference. You had a hand crank. I have relatives who broke an arm. You pull on that hand crank, and if it kicks back on you, yeah, there goes your arm. So you would hand crank the car. That would be good. We would all be a little more burly, right? But people realize that's a lot of work. We have a generator on the car that's generating electricity, because we talked about the internal combustion engine, and you have a spark that starts the fire in the pistons in a gasoline engine. So you have to have electricity. So there's a generator. So the generator was built something like this. You have a loop in a magnetic field, and you rotate that loop. The engine running is what's rotating the loop. And as it rotates the loop, the magnetic flux is constantly changing, because magnetic field's pointing like this. If the coil is like this, how much flux is going through my hand if the magnetic field is going the direction my finger's pointing? How much of my finger is going through the palm of my hand? It's not at all, right? Because palm of my hand's direction is up, my finger's horizontal, those are perpendicular. So there's no flux here. But as it turns, now I have a big flux. So there was a change in flux. According to Faraday's law of induction, that change in flux results in an induced voltage. My son gave up on me. He's walking away now. So we have that induced voltage. Then it goes like this. The flux is back to zero. Goes like this, has the flux the opposite direction. And so it's going to producing flux. Notice the change in flux is going both ways. So the voltage is going to go positive, negative, positive, negative, positive, negative. Now anyone right now is thinking, but we have a battery to store energy, and the battery is just positive and negative. It doesn't go back and forth. So they have to do something to it. And we'll talk about that in a few slides. It's producing what we call alternating current. Well, people realize we have this generator that's producing the alternating current. If we put a battery in the car, we can store some energy, and then we can use that same generator as a motor. What's the difference in the generator and the motor? In the motor, you're providing the energy to the coil. You're putting current through the coil, and that's creating a torque. In the generator, you're putting a torque on the coil, and that generates the electricity. So we can put electricity through the coil and make the generator work as a motor and start the car. And so you have a design now that you have one generator / starter. Well, then people said, hey. First of all, it's probably putting too much wear and tear on this one device. Second of all, we can optimize. In your car today, you do not have a generator. What do you have to generate electricity if it's not a generator? Anybody know? Anyone here in the cars? You have an alternator. Now, when I first started teaching, I didn't know the difference in a generator and an alternator. Fortunately, my first year as a teacher, it was college days, and my high school physics teacher was there. And I said, Mr. Bird, what's the difference in a generator and an alternator? I felt a lot better when he was like, I don't know. But now I know the difference. The difference in a generator and an alternator is in the generator, you have a fixed magnet and you're rotating your coil. In an alternator, you have an electromagnet that has interleaving fingers on it, if you will. And so one side's north, one side is south, and that whole thing is rotating. And then you have little pickup coils that are here on the center. And so you have the magnetic fields coming by, and because of the interleaving, instead of it taking one rotation to go from north to south back to north, It takes like 1/20th of a rotation to go from north to south back to north. Remember Faraday's law of induction, the induced EMF is the changing flux per time. So if you go back and forth quicker, what's that doing to the voltage you're producing? It's raising it. So this allows you to raise the voltage you're producing, and it has the added benefit that that magnet that's made out of pretty much solid metal, it has a coil on it, but made out of solid metal, is what's rotating, and your little sensitive coils are stationary. So as far as the forces, you're putting a lot less strain on those coils than you would in a generator, so it's more robust. So it's more efficient at generating power, it's more robust, but an alternator cannot work as a motor. So that's why you have alternators in your cars rather than generators. Yeah, I'm just going to skip over this because we've talked about the motional EMF and now we've gotten to Faraday's law of induction. So this here is going through the calculation of the electricity that's produced. We could get to the same answer just using Faraday's law of induction. If I use Faraday's law of induction, the EMF is equal to, I'll throw in the minus sign, the change in magnetic flux over change in time. Magnetic flux, though, is magnetic field dotted to area. So in a generator, your area is constant, your magnetic field is constant, it's only the angle that's changing. And so the change in flux is going to be equal to just, well, change in flux per change in time turns out to be BA times sine of omega t times omega. So that's, I don't need a divider anymore. It's a calculus step to go from this equation to this equation. So that's kind of abbreviated. But the EMF is just going to be omega, the rate at which it's rotating at angular velocity, times magnetic field times the area, times sine of omega t, where omega is the angular velocity. Now that's if you have one loop. What if you have multiple loops? If you have multiple loops, your flux, and you'll see the end put different places, sometimes outside, sometimes in. I'm going to put it inside. So it's omega NBA sine of omega t. That's the EMF that's produced by a generator if it's moving at angular velocity omega. So the faster it's rotating, the higher the voltage it produces. The more it turns, the higher the voltage, the bigger the magnetic field, the bigger the area. All of those produce a higher voltage. And so it's, yes, the women's NBA, omega NBA, is the maximum voltage you can produce with the generator. Once again, it's alternating, it's going positive and negative. For our cars, we don't want that. So what can we do? Well, one thing we could do would be use a split commutator again. A split commutator would allow me to reverse the polarity every time it goes negative. And so I would have what we call a rectified signal. There's another way of doing this. The other way of doing it is using what we call diodes. Diodes are essentially little devices that will allow current to flow one way and not the other. And so you make what we call a diode bridge. And right now you're all, what is he doing? That looks pretty silly, right? Okay, I cannot get an affirmation on this. What I have, this symbol right here, that's the symbol for an alternating current power supply. So my generator is an alternating current power supply. I take one side and I go to a place where I have the straight edge and the block. current can go the direction of the triangle. So if I have this side is positive, then I'm going to have current go like this. If that side's positive, this side's going to be negative, and current would go like this. And so what's going to happen is this side here will become negative, and this one will be positive. When my alternating source goes the other way, so when the bottom becomes positive, then the current is going to bring it over to the left, and it'll stay, the positive is the same. So this side will always be positive, this side will always be negative. So that's a diode bridge. That's actually what we use for rectifiers in our cars, is the diode bridge. Now there's something else we use. This produces a voltage like that. We don't like the voltage to be wiggling around like that. So we want to regulate it. We've already seen a device that will store charge separation and help us regulate the voltage. What was that device? A capacitor. So if we take a capacitor and we put a capacitor in here, that capacitor is going to make it so it goes like that. It'll discharge some, but not very much. And so that gives us a much more constant voltage, causing us a lot less problems, things like interference with our radio and that kind of stuff. So you have a voltage regulator that's built into your alternator that is rectifying, making it so it's always positive, and then using a capacitor and a little other circuitry to make it so it's very well regulated. So it's a very smooth voltage that should be coming out of your alternator so that you don't have fluctuating voltages in your automobile. This is very practical, useful things. Now, are you going to go build yourself a generator or an alternator? Not unless you're MacGyver, but it's something that very much benefits your life. So, clicker question. What two parts are necessary for an AC generator? And yes, this is 2 items. Put in your 2 answers and hit enter. I actually made it so you could enter more than 2 because I wasn't thinking, but there are only 2 that are correct. Christian, Amanda, okay, Amanda, Brandon. All right. Six, 7, 5, 7, 13. Well, there were 2 correct answers. This one that we had 2/3 of the class roughly answers one of the correct answers. You need that rotating coil. What does the rotating coil need to rotate inside of? Somebody who's really confident blurted it out. Okay, not very loud, but she's right. You need a strong magnetic field. Those are the 2 things you need. Electric field, that wasn't, you're going to create an electric field, sure, but that's not part of what you need for the electric generator. You need a magnetic field. Magnetic wires? No, magnetic wires would be a problem. They would cause us difficulties. Split commutator, when do we need a split commutator? When we want direct DC, direct current. Direct current DC. When we want direct current, that's when we have the split commutator. Or when we wanted a DC motor, we needed a split commutator. All right. Now, this slide you might realize came before the official introduction of Faraday's Law of Induction, but now I'm looking at it after we've talked about it, we can understand it better. Faraday's Law of Induction says that a changing magnetic flux will induce an EMF. So in this set of pictures, we have the magnetic field got stronger. If the magnetic field got stronger, is that going to constitute a change in magnetic flux? Yes, it will. Because the magnetic flux is the magnetic field going through. The magnetic field is all going through here because the direction is parallel to the area. So we have, in this case, going from the earlier time to the later time, an increase in magnetic flux. So that's going to induce an EMF, induce a voltage. And it's going to create a current. And according to Lenz's law, which direction is that current going to flow? First, before you say clockwise or counterclockwise, what's Lenz's law to help us decide what direction the current's going to flow? It's going to create a magnetic field opposite the change in flux. So the flux was going to a stronger magnetic field that direction. So what direction is the induced magnetic field going to have to point? Opposite direction, coming out. And so then using my right-hand rule, what direction is the current flowing if it's going to make a magnetic field coming out of the screen? It's going to be counterclockwise. So we can take Faraday's law of induction to determine how big it's going to be, and Lenz's law to determine the direction of the induced magnetic field. Yeah, all these pictures are things we saw before with the electric flux. I trust that everybody has a memory that goes that far. So our next question, what will not produce a magnet? It's not select answering. What will not produce a magnetic field? So two of these will, one will not. Okay. We had 12, 6, and 1. Now this is troubling because one of them clearly does produce a magnetic field. The magnetic field is clearly going to be produced when that happens. It clearly does because Lenz's law says a changing magnetic flux is going to induce a magnetic field that's opposite to what was there, or to the change. So that means it's going to induce a current that creates a magnetic field. Now, the other two are actually problematic. Moving a wire through a constant magnetic field. Now, if it's just a wire and it's not part of a loop, it would create an electric field in the wire, but you don't have current actually flowing except for at the very instant you start to move. And so you only would have a magnetic field generated the first instant when you start to move, unless you're accelerating. And the last one, moving a coil through a constant magnetic field. Well, if it's just moving like this, it does nothing. Now, if it's rotating, which is what I meant to say, then it would be alternating, creating magnetic field forward and backward. So my wording here was flawed. The correct answer was supposed to have been, it was supposed to have been this one here, because this was supposed to be rotating. It's still moving, but moving you tend to think of as translating rather than rotating. But changing the magnetic flux through a stationary coil is definitely going to create an induced magnetic field. All right, that's the end.